ultimately. But sine square of x is also then between 0 and 1, because square, sine of x is between negative 1 and 1. But if you square it, it'll be greater than or equal to 0, but still less than or equal to 1. But it keeps changing, so it's not going to be decreasing. So you can't use integral test. Now, even if you can use integral test, you don't know how to integrate this, right? You don't know how to integrate sine squared of x squared. Anyway, integral test cannot be used. All right, it's useless. Then how do we show that this is either convergent or divergent? Now, as I said, we know that this is between 0 and 1. Dividing all sides by positive number n squared. What do you have? So this is just 0. Positive series, right? Positive means non-negative. And this is always smaller than this. And this is very nice series. We already know the result. What is it? Is it convergent or divergent? Do you remember? P series test, 1 over n to the p power, 1 to infinity, is convergent when p is greater than 1. Divergent if p is less than equal to. So it is convergent because p test. P-test. Okay? P-series test or P-test. P-series test. Okay? Because your p-value is greater than 1. Now, larger one converges. Does not go to infinity. Plateau somewhere. Therefore, by comparison test, this gotta be convergent too. Smaller one definitely converges. Okay? Now, sometimes comparison test is very, very easy to use. But I gave you in the bottom of the section, I gave you this example. Okay? So, let's say, I'm going to change the example a little bit. Let's say you have this. And start from 2 to infinity, let's say, because when n equals 1, you get 0. Compare this. 2 to infinity. 1 to infinity was convergent, therefore 2 to infinity definitely convergent. This is behaved almost the same way. And this one converges. So it is very tempting to say that this is also convergent, because this is convergent. The problem here is, this is not smaller, this is, look at this. N squared minus 1 is smaller than n squared, both positive. If you take reciprocal, then you have to switch the order. Oops, this is smaller, I'm sorry, smaller. Therefore, this is larger. So even if you show that this is convergent, this is convergent, this is a larger one. So you can't say that this is convergent only just because some smaller series is convergent. That's the warning I gave you here, right? So you can't use comparison test using 1 over n squared. Okay? Now there is some clever way of doing this using comparison. You compare this one not with this, but 2 over n squared. Yeah, you can adjust. But there's other ways, different ways, which is actually turned out to be very, very useful for more variety of cases. That is called limit comparison test. Okay? Limit comparison test. Now, before we do limit comparison test, let me go over this. Let's say your Bn is, let's say, you learn this one. If this one is convergence, okay, then any constant, C is any constant number, this also converges, and the value will be this, right? Constant multiple of convergence series definitely convergent, because that infinite sum times that constant will be the value. Okay? Limit comparison test is actually, this is the underlying reason. Okay? So, let me write it here. Theorem 4. Limit comparison test. Limit comparison test. Now, so here we are considering limit of an and series of an and bn, and your a and bn are ultimately positive. It has to be positive series ultimately. Okay, and what is the other condition? Somehow limit of this ratio of two sequences, an over bn, is c. And c is positive. Some positive finite number. Okay? If that is the case, then see, if you have this relation, they are both positive, ultimately at least, and the ratio of the limit of ratio sequence is finite number, finite positive number, then the convergence of this, if and only if convergence of the other. Okay? Okay. Now, let's look at this. Why is the case? We cannot prove this one rigorously, but I can give you some intuitive ideas why this one makes sense. Now, think about this. Limit of an over bn is c. What does it mean? It means an over bn is almost same as c for sufficiently large n, for all sufficiently large n, because this one approaches c, almost same as c, right? So that means an is almost c times bn for all sufficiently large n. This means for all, right? Upside down a means for all sufficiently large n. So they are almost constant multiple of each other. Or you can write it, bn is 1 over c an, because c is positive number. They are almost constant multiple of each other. We saw that constant multiple of a convergent series is convergent. Constant multiple of divergent series is also divergent too. See? This is why. So linear comparison test says that if the ratio of the two underlying sequences has a positive value as a limit, finite positive number as a limit, that means essentially toward the end, they behave just like a constant multiple of each other. So that if one series is convergent, the other is convergent. If one series is divergent, then the other series is also divergent. Same fate. Okay? That's what it said. Then we can use this limit comparison test here. So, example 4. What about this one? 1 over n squared minus n minus 1. See? Now, we are going to compare. Now, think about it. In the denominator, n squared is dominant ones. We know that this will behave almost like 1 over n squared. And 1 over n squared behave, we know that that is convergence series, P series test. So we have a hunch that this must be convergence series. But how do we show that? When this one is smaller than n squared, just like this, greater than this one, right? So then convergence of this one doesn't necessarily mean the convergence of the largest series. So direct comparison test. It's something called direct comparison test. Comparison test does not work. So here we're going to use this limit comparison test. Our series is Bn. Then what do you see? Limit of An over Bn. What is it? Limit of 1 over n squared, reciprocal of this. What is the limit? 1 minus 1 over n minus n squared. Okay, positive number. And series of An converges. P series test, P equals 2. Therefore, by limit comparison test, the given one also converges. Alright? So it is quite convenient. So, this section we cover a lot of materials. It's a long section. Okay. First, we learned about integral test, right? And we use it to prove one of the convergence or divergence. And then we because by combining that one with P series, a P test of the improper integral, we got P series test, right? And then we learn comparison test, and then limit comparison test. Actually, 3 different topics. The final topic of this section, the 4th one, subtopic, is error analysis of a series which can be proven, its convergence can be proven by integral test, right? That case. So, let's say, suppose that your An, A1 plus A2 plus A3 plus A4, well, this one, S, let's say this one is series. Okay, I'm going to write it. The sum of infinite series is defined as limit of partial sum sequence, right? Let's say this is true value is S. Okay? Now, where your Sn is, k from 1 through n, ak, or you can use ai. This is nth partial sum sequence. Now, so Now that is S. Means that, think about it. A1 plus A2 plus A3 plus all the way to AN plus 1, AN plus 2. Keep going. This is Sn. So if we use Sn, so Sn is eventually getting closer and closer to S. So that means if we use a large number m, Sn will be a very good approximation, very close to S, right? So S minus Sn will be the error, right? This is the error. Error, so called error of the approximation by Sn, right? Now, the whole thing will be S. So S minus Sn must be the remaining ones, right? That's why we call it Rn and the remainder. Remainder Rn is defined as true value of this sum of the series minus partial sum sequence Sn, running total up to nth term. For a convergence series, that means all the remaining terms, sum of the remaining terms. That's why we call it remainder. Remainder is just the error, all right? Now, as you can see in the picture, look at this. So if your f is continuous, positive, and decreasing ultimately, all right? The three conditions we need for integral test. For that one, and An is f of n. Now look at this. Let's say this is n plus 1, n plus 2, and so forth. If you draw this way, what do you see? This is n plus 1, f of n plus 1, which means an plus 1. So this area is base 1 times height. So this area is an plus 1. This area is an plus 2, right? Because this is n plus 2, f of n plus 2. This is an plus 2. Same thing for this, n plus 3. So if you see this, all these, some of these areas of these rectangles will be smaller than the area of the region under the graph, right? So from that picture, we know that this remainder, an plus 1, an plus 2, an plus 3, keep going, is less than equal to the area of the region under the graph. That is precisely from n to infinity of x dx. All right? And now, if we draw this way, not like this. Now, look at this. Starting from here, let's draw this red triangle. Then what? This red triangles. This one using this. Alright? So this red one is an plus 1, right? This red one is an plus 2. This one is an plus 3. by drawing this top to the right, this is always stay above the region, right? So, if you compare this, now an plus 1, an plus 2, an plus 3, all the ones, some of these values are greater than equal to the area of the region starting from n plus 1, isn't it? Right? So we got this. This is greater than n plus 1 to infinity. Okay? Assuming that this is the conversion case. Okay? So, this is what we have. Alright? And what is this? This is nothing but remainder, Rn. Alright? So, that's why you have it here. So I'm not going to rewrite it here. Alright? This is what I start. Your remainder is between this. Now think about it. This one is starting from n to forever. N plus 1 to forever. Obviously n to forever covers more area. That's why it's larger. Rn is in between. Okay? Now, the second part of theorem 3 in your notes is, now look at this. Rn is true value s minus Sn. Therefore, S is Sn plus Rn, isn't it? Okay? So I'm going to add Sn here, Sn here, Sn. Then what do you get? Sn plus n plus 1 to infinity f of x dx. Now, Rn plus Sn means true value. The sum of the series. Sn plus. Alright. So I'm going to call it double star. Now, let me check that recording is doing fine. All right. And then final example, no, second final. Example 5. I'm not going to write it, everything, it's too many words. Estimate the error involved when approximating 1 over n to the third. Okay? By using the first 10 terms. Okay? So that's A, right? Using S10. B, how many terms are required to ensure that the sum is accurate to within point A? B, how can we be sure that the remainder is less than 0.0005? Okay? That's the question. Alright? The first term shows that. So I'm going to write this one is SRN. Okay? This is the star. Now we want to use S10. Alright? Solution. We want to know the error. We want to use by using the estimate the error involved. So when you use S10, you can use calculate. S10 is n from 1 to 1 of n to the third. If you use your calculator, it is 1.1975. Okay? Now, from this theorem, the error, when you use this one as an approximate value, is R10. And then R10 is less than equal to 10 to infinity 1 over x to the third dx. Okay? Now, this one was calculated the first few lines of the solution. See that? So when you do And then we calculate this. So n to infinity of x to the third is limit t goes to infinity n to t x to negative 3 dx. So what? Adding 1 is negative 2, negative 1 half. Negative 1 half t to negative 1, t squared from n to t. So that would be 1 half of 1 over t squared minus 1 over minus. This one goes to 0, so 1 over 2 n squared. Okay? So this one starting from n to infinity 10, then this is 1 over 2 times 10 squared. 1 over 200 or 0.005. So you can say that if we use S10, the first, sum of the first 10 terms, that approximation has a maximum possible error 0.005. So this 7 is not really reliable. Alright? It could be as large as 0.1, 0.005, so 0.12025, right? Okay. And then, so because of this, then you can say that n plus 1 to infinity 1 over x to the third dx is definitely 1 over 2 n plus 1 squared, right? You just change n to n plus 1, that's all. Now, part B. We have to find the minimum value of n such that the maximum possible remainder is less than 0.0005 rather than 0.005. How many more terms do we have to add to have a smaller error, right? Now, here, so in that case, so whatever, B, if we use Sn, the error Rn again is bounded by this one, x to the third, okay, from that theorem, which we just calculated 2n squared, 1 over 2n squared. Now, we don't know exactly what that is, so we cannot control this one directly. But if we have this upper bound of the error being less than 0.005, 0.0005, I think this is 1 over 2000. Okay. If you do that, then automatically Rn will be smaller than this, right? So we try to solve this inequality. Okay? So then